Good morning. Welcome back to the course on rapid manufacturing. I am Dr. Amandeep Singh. We are in a module where we are discussing rapid product development. Dr. Ramkumar has discussed computer-aided design and computer-aided manufacturing. A brief introduction to these concepts have been given by him. I'll take rapid product development forward to these concepts. I'll discuss the overall concept of rapid product development first, then I'll discuss simulating reality of 3D print with FEA. FEA is finite element analysis. This is computer aided engineering. We have already discussed computer aided design and computer aided manufacturing a little. Now, what is computer aided engineering? The design that we make, taking the dimensions or scanning the object, we make a design. Then we need to analyze whether this design, if we select a specific material and the dimensions that we give, whether it would bear the realistic conditions or not. Then certain analyses have to be done, stress analysis, thermal analysis, fluid dynamics, all those things can help to conduct an analysis that would make the product viable in a virtual environment. What is virtual and real environment, that we will discuss when we will see rapid product development scenario at first. Then I will discuss factory for rapid product development. In this lecture, I will just introduce what is a additive manufacturing factory or a rapid manufacturing factory, but we will also see plant simulation, like we can simulate for the product. The various stresses, various parameters of the product are taken into account and are simulated before actually manufacturing the product. In the same way, we can design the factory in a simulation software and see whether our product flow is going properly or not. So, as people say, it is better to fail a simulation than to fail a real product or a real factory. So, those simulations are possible these days. First, I will discuss the concept of rapid product development. Rapid product development is a manufacturing culture which promotes the new products development from design to manufacture in the shortest time scales possible. Now, what is the aim of rapid product development? When I will do factory simulation, I will take time as the variable there, time as the main culprit that we need to address. We need to reduce the times because they are short times to market. With the present scenario, what is happening, this culture uses new technologies to promote the time decreasing, including utilization of 3D, CAD, CAM, rapid prototyping, rapid tooling and the use of new management techniques which restructure the manufacturing process. So, what is there in the present or in the contemporary scenario, worldwide competition has led manufacturers to a basic change into product development. One thing is additive manufacturing is coming into play. Second thing is the product design is changing very drastically these days because new products are coming in the market and customers are demanding the change. So, as in the first weeks we discussed that while production consumption cycle, the production and consumption keeps happening and the customers keep giving feedback and the product design, product development processes are changing. So, management techniques are also there. There is a big analytics. Analytics comes into play then. So, this is the part of simulation. We have big data these days. Big data is the large amount of data that we need to manage. So, in order to continue to be competitive, manufacturers should be able to attain and sustain themselves as a worldwide or world-class manufacturers. So for that, these manufacturers should be capable of delivering the products in time, satisfying the customers, and more specifically products of higher quality and fast to market and at the affordable or the rational costs because of the competitions. So utilization of rapid product development allows companies to launch new products into manufacture in short time scales, reducing the development costs for new products. Computer simulation and rapid prototyping technologies represent important tasks in different areas of industrial development because of its potential of cost and time saving. Now, companies are finding these techniques to be extremely beneficial and they are being adopted at a rate much higher than ever. The use of rapid prototyping, rapid tooling technologies, rapid prototyping, I can also put rapid tooling here. Use of these technologies in combination with existing in-house facilities in designing, then testing, simulating, then rapid prototyping, then finally mass production. So these technologies are being used and these technologies represent important tasks in different areas of industrial development because of its potential of cost saving and time saving. Before producing newly developed mechanical parts, the entire manufacturing process can be visualized and improved by means of numerical simulation techniques or in some cases by virtual simulation technologies. This we will discuss when we will discuss plant simulation. Plant simulation 10 software, that is also known as technomatics. We will discuss this, and this is developed by Siemens. Siemens PLM software is the name given to the broader group of modules that Siemens provide. Rapid prototyping technologies also can be used to build prototypes and mold, insert or small series of very quickly and cost efficiently. This way offers to small and medium sized companies enormous potential for improving the time to develop and market their products and for increasing their competitiveness. Now, this is the rapid product development architecture or scenario that is taken from this reference here. What they say? This is rapid product development, the external circle, the outer circle is. What do we have in between? You can see in the bigger fonts we have product research and product design. Product design is nothing but the CAD, the 3D CAD and 3D data product modeling that we saw. So, in product research, the initial design concepts and ideas. This is the product development process that we discussed in the first or second week of this course. Functionality, aesthetics, testing, assembling, design for assembly, all those things. Then developing new product, marketing analysis. The different analyses are conducted before actually designing the product. What is the need of the consumer? What are the changes that consumer need in the present product? Is it a new product? Is it a change by evolution or it is a change by innovation? Those all things we need to identify. Then it comes the product design. In product design, we make a CAD model and then we do virtual prototyping. Virtual prototyping and rapid prototyping are put parallel here, but this virtual prototyping would come first and rapid prototyping later. Virtual prototyping is the finite element analysis or computational fluid dynamics or certain other computer-aided engineering that we do only on the computer without actually producing the product. That is virtual prototyping. Now, rapid prototyping is actually manufacturing the product and testing that product in the realistic or the controlled laboratory conditions. So these two things can happen. Now these virtual prototyping or rapid prototyping or both lead to the prototypes, that is we get form, fit and functional testing, which I just said that we have this in laboratory conditions or controlled conditions. Sometimes in realistic conditions also this happens, like Hero Cycles, that is one of the biggest cycles manufacturing company in the world. When they come up with a very new product, the first product, the prototype they develop, they sell it to their internal customers. Internal customers are the people who are closely related to Hero Cycles, maybe milk vendors who are supplying milk within the factory, or the people who are the employees of the factory, or other people who are closely associated with them. Then from the internal customers, they get the feedback and try to see what is the change. If the change is there, is that change required, then they inculcate that change and then produce the product to make it reach the final consumer, end user, to the masses. So that is prototypes. So we get the form, fit, functional testing of bikes in this case. So that can happen. Also simulation happen here as well. So here we have simulation, and after simulation full production tooling and rapid tooling is done. Full production tooling for mass production, for big size production. Then manufacturing proceedings, that we get a final manufacturing, then product launch and release into the marketplace. So this is the final step. In between, what is this circle doing? This is knowledge management. Knowledge management is new field that is coming up. As I said, data analytics is one thing that managerial tools are to be conducted. Internet of Things is there, IoT. Actually we have data. A lot of data is already available in many forms, documents, internet, catalogs, journals. From the data, some information is extracted by the people and that is also recorded. But to extract the knowledge from the information, knowledge is something that has some applicability. If we apply information, that we can call as a knowledge. Knowledge is something in the mind of the experts. They have the knowledge, they don't have only information. When we collect multiple pieces of information and something come out as an application that can be used, that is known as knowledge. So this knowledge management, which is now a formal subject in many universities, subject of study or course of study, that is encapsulating all these things. Right? This is rapid product development concept. Next, I like to discuss the computer aided engineering. In this, I'll just take an example of a 3D manufactured, 3D printed product that is a lever that is used to take the piston off from a machine. That lever was made of a metal before, now it is produced from a polymer. Which polymer we selected and how the finite element analysis happened there, that we will discuss. So simulating reality with finite element analysis, FEA is finite element analysis. FEA is again a complete course in itself. We can't discuss the details or the complete explanation of finite element analysis of computer engineering in this 1 hour lecture. But yes, I will try to introduce you to the overall idea what computer aided engineering does. Finite element modeling in many ways is more like an art than a science, since the quality of the results is dependent upon the quality of the model. One of the more common errors that a beginning finite element analyst makes in modeling is to simply simulate the geometry rather than to simulate both geometry and physical behavior of the real structure. If we only simulate the geometry but not the physical behavior, geometry is just a size. Okay, I need to manufacture this pen holder, it has this diameter and this and this some diameter, smaller diameter, bigger diameter, this curvature, all these things we can scan this, and that is geometry. But physical behavior, would it be able to hold this pen? What is the strength that is required? This is actually a stylus here. So, do we need to put a battery in here? So, what are all those things required? Do we need to provide some rubber, some anti-friction coating here so that it does not slip on the table? So, all these physical behavior are to be simulated. Now, simulating reality with FEA, the learning objectives in simulating reality are: number one is creating simulations. Creating simulation is, do we need to do stress analysis or thermal analysis or maybe model frequencies, right? Then we can have static stress, static and dynamic stress. Here dynamic means kinematic. Then we can have thermal and thermal stresses that is discussed. Then maybe shape optimization. Shape optimization, that what exactly should be the shape of the object that we are trying to produce. Then structural buckling if it is there. Buckling is a phenomena that is more associated with columns. Buckling of columns is one of the subjects that is taught in mechanical engineering, specifically in civil engineering and construction. It is actually when column is subjected to load from both the sides, a compressive load, it tends to buckle from the center. That is known as buckling. So, structural buckling, this can also one of the simulation. Other than that, we can have event simulation. So, this I will specifically discuss again in plant simulation. Okay. These simulations can be created, and in this presentation we won't discuss all the simulation, but specifically we will discuss stress analysis, stress, or I would put static stress only. Static stress, and along with static stress we can also discuss some about the shape optimization. Then second objective is assigning the materials. When we are conducting the simulation, we can select different materials. For instance, what first thing is the process that we are choosing and the material that we are choosing, that should be having compatibility. For instance, if I am choosing laminated object manufacturing, I should have a material in the form of sheets. If I am choosing 3D printing, I should have material in the form of wires feedstock or in the form of powders. So, those things are to be taken into account. Assigning materials, then setting constraints and loads. Constraints and loads are again the same example, the loads that the buckle are subjected to. These constraints, that the load would be from this side, equivalent load would be there, what will load on the in the ends and in the center. For that, one should know the physics or the science behind the research. These simulations are always GIGO, garbage in, garbage out. Whatever input you give, the output will come accordingly. So, a researcher or a simulator or an engineer has to know the basic sciences or the GUI, as I say, graphic user interface of the software. Sometimes, though there are softwares that have proven to be very intelligent and one need not to understand the complete GUI of that, they have proven the results to be very effective in realistic conditions, that can be trustworthy. But an engineer should better know the sciences behind the inputs that is his or she is giving. Next is interpreting this simulation result unless you know the science, or I would say physics behind the outputs that are coming or the results that are coming, we cannot interpret the results. So that is important. So these are the things which are generally covered in computer aided engineering. Now this class is designed to familiarize you with some of the simulation tools. It is not a replacement for a solid understanding of finite element fundamentals. The principles of logic, physics, a good engineering always apply. As I said, be careful when creating simulations. They can be subjective, and poorly defined simulations will result in poor simulations. Again, GIGO, garbage in, garbage out. This is the product that we have taken. This is a lever that is need to be designed. This is the final product that we have obtained. Our purpose in this was to reduce the print time, because this is a 3D printed product. Also, we needed to reduce the cost. We needed to consider the material usage and consider alternative materials as well. Original design considerations. What original design considerations are there? Originally, what person do? He has to have the knowledge of materials and have to do hand calculations, and inventor models has to be carried out. But in simulating reality with a computer software, this is actually the Autodesk software. Specifically, we have used Fusion 360 software to develop this modeling, and some of the slide content is taken from the Autodesk website only. First thing is selection of material. One material for this product could be polystyrene, or other could be ABS. Polystyrene, the properties were hard wearing, high thermal resistance. ABS was cost effective because of its close availability and low cost as well, and it has a quicker print time. Now these are the properties which are the files inbuilt in the software. These are called the material libraries. Or we can have certain libraries in the software that carries the information that can be used to put the input. Also, we can generate our own material and our own simulations in certain software that provide the provision for this. Now this polystyrene has this density. This has density a little larger than polystyrene. The Young's modulus or the strength is a little higher in polystyrene, and in ABS it is lesser. So these are all material properties. We have already discussed what are the kind of materials, and specifically which material to be chosen, that can be finally decided when we do finite element analysis. Now first thing is, what is meshing? Meshing is, as we have seen in the 3D scanning, when we scan the model, point cloud is obtained. From the point cloud, different points are joined together by the software itself, and they create a mesh. At least 3 points are there, 3 points would make a triangle. So that is known as mesh. So what are different kinds of meshing that we produce? This is 3D meshing actually. This is 3-dimensional meshing. One is tetrahedron, another is pyramid. If you know the shapes, tetrahedron has 4 faces, all the 4 triangular, okay, 4 triangles. Pyramid has 4 triangles and 1 quadrilateral. Triangular prism has 2 triangles and 3 quadrilaterals. Hexahedron has, it is kind of a cuboid, it has 6 quadrilaterals. So these are the different options available in different softwares. When we select, first is tetrahedral. Tetrahedral meshing we will select. After tetrahedral selection, we can have linear tetrahedral, that is with 4 nodes, parabolic tetrahedron that has 10 nodes, and parabolic tetrahedron with curved edges, it again has 10 nodes. It all depends about the experience of the engineer who is conducting this simulation, what kind of product do we have and how dense meshing do we need and what is the specific strength that we require. For instance, in this product we will see that there are holes. This is actually a lever that will be taken and be fixed to something. So, these two ends should have higher strength at these points. At the center we will see where is the loading happening, when one is pulling the lever, pulling the piston or pushing the piston in. So, this is attached to that. So, here we need to have a little denser meshing, and at the corners also we need to have a little denser meshing. Let us see how it is done. So, in meshing, this is selected tetrahedron, then parabolic tetrahedron with curved edges is selected, and this gives this kind of information. We selected parabolic tetrahedron as an option, and the maximum turn angle, all these parameters are set, maximum adjacent mesh size ratio, maximum aspect ratio, these are sometimes default and sometimes it is set. So, this is a mesh that how it looks like in a solid model. Again to be noted, this is a 3D mesh. Next is creating a simulation. What are the inputs to the simulation? Every simulation needs 3 key inputs: materials, constraints and loads. So, in this software these 3 inputs are just here of one after another. It is actually giving everything in a sequential order in this specific Fusion 360 software. First we need to put what is the study we are going to do, then what material is there. After selecting the material, we can put the constraints that we need to identify, then what are the loading conditions, then what are the contact points, what do we need to display, what do we need to solve, thermal analysis, static stress, buckling, etc., and what are we trying to print here, what do we need to manage, finally what results we need to obtain, and finally we can inspect or validate. So, this is the sequence of input that is going on here. So, these are the major 3 constraints that we will work on: material, constraint and load. First thing is material. Materials for the simulation can be of different types. Like first, when we click material, this window pops up. For all libraries, we select the material libraries, and for the component is named component 1. ABS plastic is selected, and this ABS plastic selected, so we can also select the safety factor. What do we need to save here? Yield strength, because we are doing static stress. Static stress analysis has to be done. So, we need to fix the yield strength here. So, we need to put yield strength as a factor here, safety factor. Next is constraint. After material, we have constraint here. So, what are the constraints those need to be fixed? Is it fixed constraint, frictionless constraint, pinned or prescribed displacement? Fixed is that prevents the movement in the selected by default all directions. Frictionless is prevents movement normal to the surface. Fixed is, for instance, there is some screwing that is happening. It is fixed at this point. Some screw is there. It is fixed. We fix it here. It cannot move at all. So, the point where holes were there in the end of the levers, it is fixed. Frictionless is when we need to slide something, and it prevents movement normal to the surface. Then pinned is kind of a hinge when it is moving something like this. Pin is something, for instance, this is pinned here and it can move like this. This is pinned. It is pinned here. At this point it is pinned and it can move like this. So, this is pinned. It prevents the movement in radial, axial or tangential directions. Then prescribed displacement, this is similar to fixed with defined prescribed displacement for every fixed direction. So, in fixed kind of a choice, in all directions the movement is fixed, but in prescribed we can change some of the movements to frictionless or pinned or non-constrained. So, these 4 options can be selected. So, we selected fixed at the ends. Then is load. Load, what kind of loads are to be put? Structural loads, linear loads, angular loads, toggle gravity, edit gravity, all these options are available. Then we put the loads, specific loads, those are there. So, these are the load definitions. We can put force, pressure, bearing load, movement, remote force, gravity, etc. What specific magnitude of force apply on faces or edges. So what is the normal force or parallel force in pressure, what is the pressure that is applying on the face, what is the magnitude of pressure, the bearing loads, all these load types of specific magnitudes and their specific conditions are put in here. For instance, in bearing load, radial or perpendicular to axis, that we need to tell. So these load definitions are given. Now these three things are fixed. Now we come to manage. In manage, we say we need to have adaptive mesh refinement. In adaptive mesh refinement, we get this customized. Maximum number of mesh refinements is 6. So result convergent tolerance is 5% and portion of elements to refine is 40%, and this specific mesh and void merge stresses, this specific model is chosen here. So this is creating mesh settings, how mesh settings happen. So this is the right most slider portion, or the custom activates the individual input fields in the dialog so that you can specify your own customer refinement settings. The available settings are as follows: maximum number of mesh refinements, results convergence tolerance percentages, portion of elements to refine. So these are details of these three options, those are there: maximum number of meshes, convergence tolerance and portion of elements. So what is maximum number of mesh refinement? This value is the maximum number of mesh refinement and solution iterations the program may attempt. Once this number of refinement passes is reached, the solving phase terminates, whether results have reached the desired accuracy or not. This option provides a means to prevent a model with diverging on unstable results from running for an excessively long time. So when mesh refinement is maximum, it stops the program there. It wouldn't run the simulation, it wouldn't waste the time there. So this is maximum number of mesh refinements that we allow, and that is put as a value 6 here. So also solving times can become very long if mesh is refined to the point that an extreme number of elements are generated. In most cases, good results are achieved in a reasonable number of refinement steps, less than 8 for example. So mesh refinement number is generally put lesser than 8 to optimize the time of the simulation. Now results convergence tolerance. Once the percentage of change in the results between the two consecutive iterations is less than or equal to its value, to the specific value that we have put in, we have put this value as 5%, the results are considered to be acceptable. So 5% tolerance is acceptable. So that is we have put. No further adaptive mesh refinement or solution iteration is performed. For any results change greater than the specified percentage, the mesh is further refined and the solution rerun. The smaller the value is, the more accurate the results must be to complete the refinement process. Caution: if maximum number of mesh refinements is reached, the refinement process terminates whether the results convergence tolerance has been reached or not. So this is the priority that is taken by the software. This is taken later. Mesh refinement is the first priority, and second is results convergence tolerance. Third is portion of elements to refine. Refinement occurs at critical range of the model, such as where the stresses are highest in a structural analysis. This option controls how much of the model is refined. For example, at 5%, only those elements in the top 5% with regards to critical results are refined. At 50%, half of the elements are refined, and at 100%, all elements are refined. This option is not applicable to modal frequencies analysis. So this is the portion of elements to refine. 50% of elements are refined while conducting analysis. We have put this value as 40%, and convergence tolerance is as 5%, number of mesh refinements as 6. So interpreting the results. So what are the results that we expect from here? So what does the actual deformation look like? Where are the high stresses? Is there a possibility of singularity? What is singularity? I will just tell. What does the convergence plot look like? These things we need to see. So baseline target here put was Void masses. So this is the Void masses megapascal, and solution step is something like this: actual and target. Actual is 2.89% convergence rate. So mesh convergence. Generally, an overly coarse mesh results in unpredicted stresses. Typically, displacement results are less sensitive to mesh quality and density than stresses are. When the stress change becomes insignificant between two successive mesh iterations, say less than 1 or 2%, you can have or you have achieved what is commonly called mesh convergence or result convergence. That is, the finally mesh convergence has happened and final results can be seen or obtained. So this is what it is telling to say. You can read this all. Now singularities. What is a singularity? Finite element analysis uses a theory of elasticity, that is, stress is equal to force per unit area. No matter how much we refine the mesh, the area will remain 0. So if the area is 0, then stress is infinite. So this is known as singularity. At some specific point, it is like a black hole. At some specific point, it shows that it is a very high stress, so infinite stress. This is known as singularity. So these are the certain issues that finite element analysis person faces. There are certain errors that could happen while we are conducting this FEA analysis, finite element analysis. The modeling errors due to simplifications, we try to model for the real world and yet not able to do it 100%. More simplifications is sometimes leads to error. Sometimes discretization errors that reside from the creation of mesh, that discretization or the division of mesh is not proper. Then numerical errors for the solutions of the equations, those we are putting here. So these errors can be many. This singularity is also one of the issue, I would say. So a finite element model will sometimes contain this kind of singularity when the stress is very high or infinite at a specific point. So this is singularity. Singularity can be confusing because it may cause an accuracy problem inside the model, which implies a problem with visualization because singularity extends the range of stresses. So it has extended the range of stress here. This means that smaller stresses can appear to be negligible. Let me put a number. This is 1,000,000 units of stress. So this is only 2 units. So this looks to be negligible. So this is why singularity is a problem here. What causes singularity? There are certain causes of singularity. The basic cause is the boundary conditions sometimes are not put very fine. So we are not having any singularity in our product, but just to give you an introduction what is singularity, I have put this slide. Now creating simulation. In this specific product, we will create a simulation, and this is the first step. We just take the product and test joint V1 is the name given to the product, and we have selected the specific document settings, and this is the body that is generated. Then we apply the constraints. The structural constraints, as I said, these are fixed. This cannot move because it has to be fixed. There is a hole here, hole that has to be fixed with a screw. That is why these are fixed. Structural constraints are there, fixed one. Then we apply load. A bearing load is applied here. Bearing load is this can move in this direction and this direction. Okay. Then it is applied on one face, angle can be 180 degree. This bearing load is applied. Then is shape optimization. In shape optimization, you can see that this is the load path criticality. What specific shape? So we can see the maximum load. It is showing mass ratio from 0 to 1 here. So the maximum load is at these points. Next is joint analysis. In joint analysis, we added this 1 versus a target. So actual was 2.89% and target was 5%. So I have a video for you here, a short video. You can see the joint analysis, how the joint moved. This is how it moves. So this is the animation that is there in the software. So next is joint report that is generated. In joint report, we finally get this specific material and the summary is there. So safety factor per body is 3.448 as minimum and maximum is 15. So the different principal stresses, first principal stress, third principal stress, then stress is normal to XS and YY and ZZ planes, then shear and XY and YZ and ZX planes. So all these parameters are printed here. Finally, we make a comparison between the properties of the initial and the final joint that we are doing, joint 1 and joint 2, the two shapes of joints. This is shape 1 and shape 2. In this you can see this hole is larger, this hole is smaller, this width is higher, this width is lower. These two were compared and print time for joint 1 is 30 minutes, print time for joint 2 is 19 minutes. So this filament uses 3405 of millimeters. In this case the filament uses lesser. Both joints are acceptable, but we are having lesser time in this, and also the strength is acceptable. So this is finally selected. So this is a broad example of finite element analysis. We can conduct a detailed analysis on thermal or on many other different parameters. So I haven't taken all the parameters, just an introduction part was this. Next is factory for rapid manufacturing. This is a figure that is taken from additivemanufacturing.com. It is showing different sections. This is the additive manufacturing section, this is CNC sections, this is a sintering section, this is texturing section. It is showing the kind of a layout that is known as process layout. I will just brief the layouts when I will discuss the simulation, plant simulation. So this is a process layout. It is showing that additive manufacturing is one part of the factory in the present scenario where we already have different machines here, different setup. Additive manufacturing can be put as one of the sections where only additive manufacturing happens. So this is only one process, additive manufacturing. This is only CNC machining. This is only sintering process that is happening. So this is the kind of a process layout. However, the complete additive manufacturing process can have different additive manufacturing machines in one section. For instance, this is all 3D printing. The second one is all selective laser sintering. This third one is all laminated or sheet manufacturing. So these all can be there. What it is showing, this is again an illustration taken from the EOS Systems, which is a big company that manufacture or provide the software suites and the hardware for additive manufacturing. They have given this connection with the cloud. So this is the factory for future of digital manufacturing. We get the data from the cloud and the data is being provided to all these units separately and the manufacturing is happening. There are a very less human intervention and on the shop floor in working or interacting with the computers and designing there, and the data is just transferred from the cloud here. So this is a clear presentation of that. EOS Connect, EOS Print, EO State, EO System. So these are different suites, those are provided by EOS. For instance, EO State, this one is an automated and intelligent multi-monitoring suite that enables customer to conduct a real-time quality assurance of all the production and quality relevant data. It is composed of 4 different monitoring tools, for instance, system, power bed, melt pool, exposure, etc. Then EOS Print is an open and productive CAM tool. This is a CAM tool. It is showing it here. It is a design simulation, CAD, CAM, and NX design is there. CAD and CAM tool, it allows the business to optimize the CAD data using EOS system. So it supplies the data and does all the analysis that we just discussed, finite element analysis, other analysis, and put the data here. For where this data being received, you can see the directions. This is in either directions. So data is being received from different modules. It is web based design, you can say web based or telecommunicated design, in which Internet of Things, IoT, Internet of Things is playing a part. So with a bundle of new features that enhance productivity, such as Z segmentation, a specific unique exposure patterns, all those things are coming these days. So these are different features, those are coming in the current systems. This EOS Connect, as I said, is very important. They are not only solutions that connect with enterprise resource planning, but also serve upcoming digital marketplaces or Internet of Things platforms. So this is the next step towards a comprehensive or user-friendly machine park surveillance. So this is happening. Also, an extensive research is done by Lan in 2009, and he developed an web-based rapid manufacturing architecture. What he said, from internet, customer or firm or service bureau or collaborative service system can provide the information, and this information is provided using some website of the manufacturer, and they use various tools. Various job templates are already available which interact with this. This is the main thing, web-based website that is interactive with them. So they have the ASP tool set, process planning and job management. This is all the factory part. So this is customer. This is our, again, the part of factory only, and manufacturing. This is actually completely, this is factory. So here we have CAD, CAE, all those things, and here we have manufacturing. So what it is telling, that the database that is already there, that rapid prototyping and equipment are there, all those data points, client task, client information, they interact with the different machines those are available, and different parameters are taken into account, that is build time estimation, online code system, optimization of part orientation, support structure. These are different parameters. Then what they need to do, they need to manage the job as well, that is manufacturing resource management, job collaboration, then process management, client management, and they finally give the input to the manufacturing, that is computer aided manufacturing, in which the CAD workstation is there. CAD workstation can be here as well. In the second part, I will put this part 1, part 2, part 3. CAD can be in part 2 and part 3 both. This is reverse engineering equipment. The CAD workstation can be in part 2 and part 3 both. And after CAD, we have reverse engineering equipment and rapid prototyping equipment and rapid tooling equipment. So finally, rapid tooling happens, and after rapid tooling, the final product is taken to the mass production. So this is hardware section. It is mentioned very clearly. This is the software section. They are putting it software section, the second part. This is hardware section, the third part. Okay, this is the web-based manufacturing. That is new concept that is being applied by many of the industries. Now for this kind of this setup, the present skills of the manufacturer or the production people would not work. We also need to have the specific labor. One of the concerns that is perceived as the largest is a presumed skills shortage to work in the new factory environment. It is true that these new machines will now need an additional skills for operators, and it's imperative that companies train engineers, industrial specialists and managers through continuing education programs or at universities and training centers to keep up with breakthrough additive manufacturing technology. So this is a good news for the students or the people who are taking these courses, that these skills are required for the present scenario that is coming up. The future of manufacturing is digital manufacturing that needs the skills from all the different streams, or not only in engineering but also in data management, in designing through website and different modules, the customers changing demands, what are the marketing strategies, all those things need to be learned. So as factories become fully automated and production equipment becomes more independent and self-sufficient, the roles and responsibilities for the workers will change, and managers and engineers will have to adapt the present scenario, present situations. The industry leaders need to make sure that the workforce adaptation is smooth, making the transfer of expertise from within their ranks to a company's workforce is a rapid and pragmatic. Because we are talking about rapid product development, we cannot have any leverage in the skills as well. We cannot allow any weak points here. So this is all supply chain management that we are talking about, where human resource is also one of the link of the chains. The best example comes to the fore on the technical side, where simply understanding what additive manufacturing related sensors are seeing inside the 3D printed parts or products is critical to ensuring their quality and reliability. Additive manufacturing system manufacturers create quality and reliability monitoring tools that have intuitive user interfaces, but technicians must go through adequate training so foreign tools feel natural to them. So, this training, continuous training has to be conducted. So, beyond the new technical skills already emerging, other roles need to be filled, including chief intelligence officers who grasp the machine intelligence, shift supervisors who manage machines, not only people who manage machines as well, and the people with them, industrial and designers who redefine the factory floor to accommodate automation and new additive manufacturing equipment and processes. So, this is the factory for rapid manufacturing, and also I have touched a little about digital manufacturing. So, to recapitulate, we discussed what is rapid product development, we discussed what is computer-aided engineering and certain steps in it, we discussed what is rapid design for rapid product development. So, this is rapid product development process, and we have discussed these issues here: rapid product development, computer-aided engineering, and factory for rapid product development. Factory for the additive manufacturing. We will discuss the factory simulation in the next lecture, and also we will see what is the factory, what is the kind of layout that we can choose specifically for additive manufacturing, and how event simulation can help to simulate the realistic conditions in the computer only. When we use specific software, we will use Siemens Technomatics software. So, this is rapid product development, and we have covered these topics, as I said. Also, in rapid product development, I will just like to list them again. One should be share about the product design and planning. Number 2, the product architecture. Number 3, product specifications. The difference between architecture and specifications is that in architectures we define the product requirements, scope, gather the data, manage requirements. In product architecture, we translate and realize the functional requirements, determine the types of product architecture that can be used actually. And in product specifications, we establish the target specifications, we refine the specifications, and functional analysis is conducted. After this, the DFM, or design for manufacturing, design for assembly, all these things we have already discussed in the previous lectures. Then we come to the computer aided design and computer aided manufacturing and computer aided engineering. So, this includes prototyping, rapid tooling, and all these things, and also we need to have factory or plant design. So, this is what we have discussed in rapid product development. Next, we will take the product lifecycle management. First, I would like to introduce to product lifecycle management in the next lecture. Then we will go to the plant simulation. So, let us meet in the next lecture. Thank you.